Can you hear me? Okay. Okay, we'll get started. We were discussing Bode plot in the previous lecture, and we talked about second order Bode plot for the second order transfer function. Today I'm going to talk about general Bode plots. So let's say I have a transfer function k s plus z1 s plus zm over s plus p1 s plus pn. Then we had seen in the previous lecture that 20 log g of j omega is the same as 20 log k plus summation 20 log absolute value of j omega plus zi I equals 1 to m minus summation k equals 1 to n 20 log absolute value of j omega plus pk. So the Bode plot of transfer function is sum of magnitude of different Bode plots, and then angle of gj omega also satisfies the same expression. So let's see how is this useful. I need you to take out this handout that I distributed in the previous class and go to the second page, second column. Okay. And let's look at a transfer function g of s equals to k one plus s over z over 1 plus s over p. So we want to draw the Bode plot of this particular transfer function, and for kicks let's assume that z is less than p and they are all positive. Okay. Okay, so we want to draw the Bode plot of this particular, an approximate Bode plot, not the exact Bode plot. I want to draw an approximate Bode plot of this particular transfer function. So I have three terms here, k, 1 plus s over z and 1 plus s over p. Going to the Bode plot, the 20 log k, so the transfer function, or the Bode plot for k is just, this is 0 degree and this is 20 log k. The Bode plot for the 0 is given by this is my z, zero degree, 90 degrees, this is 0, and the slope here is 20 dB per decade. This is Z over 10. This is Z 10Z. Okay. So we have plotted the Bode plot corresponding to K here, 1 plus S over Z. So this is and this is Bode 1 over 1 plus S over P. Okay, so I drew 3 Bode plots for each of those components of the transfer function. Okay, so now I need to draw the Bode plot of the original transfer function. So where did I get these plots from? So I want you to go to the second page of the handout. So this is the first Bode plot, this is the second Bode plot, and this is the third Bode plot. Rather the approximate Bode plot for each of these 3 systems. Okay, so that's where I got these 3 Bode plots from. Okay. So 20 log absolute value of Gj omega is the same as the 20 log of gain plus 20 log of zeros minus 20 log of poles. So I just need to add these three Bode plots in order to get the Bode plot of Gj omega. So remember that this is the Bode plot of 1 over 1 plus Sp. Okay, so it already has this negative sign inbuilt in it, because you can think of this negative sign as plus, and you can think of it as 1 over j omega plus pk. Okay, so that's why I'm just summing up all these 3 Bode plots. So the Bode plot of G would be this plus this plus this. So So that doesn't only hold only for the magnitude plot, it also holds for the phase plot, because we have this expression right here. So again, I can change this to plus, and I can change this to angle of 1 over j omega plus pk. Okay? So this is already in that particular format. So what would the magnitude plot of G look like? So I have to start from 20 log k plus 0 plus 0. So I'm going to start at 20 log k until, so remember z is less than p. So I'm going to encounter z first, and there will be an upslope of 20 dB per decade. So let me put z here, and this is my p. Okay, so I go, my gain is constant at 20 log k until I hit z. At z, I see that there is an upslope of 20 dB per decade. So I start with sloping up 20 dB per decade. And then when I hit p, I see that there is a sloping down of minus 20 dB per decade, which will cancel the sloping up of 20 dB per decade. So this will be a constant. Okay. This slope is 20 dB per decade. There is something interesting happening here, and I want someone to notice what's interesting in this particular plot. So this is an approximate Bode plot. The actual magnitude plot would look something like this. So it will almost imitate this asymptotic or the approximate curve. But there is something interesting happening here. What's the interesting thing in the slope of this Bode plot? So I have a slope of 0, and then the slope changes upwards at what point? At a 0 of a transfer function. And then the slope changes downward at a pole of the transfer function. Okay? So that's the interesting thing here, which is if you look at the gain magnitude over a wide range of frequencies for a transfer function, by looking at the points at which the transfer function slopes up or slopes down, you can actually figure out where the zeros and the poles of the transfer function is. Okay? Is that cool or not cool? I think it's cool. I would have never expected it if I had not studied this topic before. So, okay. Now the important thing is here you're seeing so this was the slope of 20 dB per decade, and now you're seeing a slope of 0 dB per decade. So there is a down. So basically the slope has changed from 20 dB per decade to 0 dB per decade. So that's why there is one pole here. Now I'm going to make a small change to the transfer function, and then I'll ask you what the Bode plot would look like, at least the magnitude plot. You know, you can draw the same phase plot in this fashion. Okay, so there is an upward slope, and then there will be a downward slope because of the pole, and you can draw the phase plot accordingly just by adding these things up. Maybe we should draw the phase plot as well. Oh no, I don't think I can draw it here because half the class will not be able to see it. So let me draw the phase plot here. This is Z, this is P, So I start at 0, 0, 0. So okay, so I start at 0 degrees until I hit z over 10. Okay, so when I hit z over 10, I'll have a sloping upwards to 90 degrees at 10z. So I reach here, then I'll have a constant slope. So this is 90 degrees minus 90 degrees. And then I'll start sloping down back to 0 degrees. Okay, so this is what the phase plot is going to look like. So I just add the phase plots of individual components and I get the phase plot of the transfer function. The actual phase plot might look like this. Let me draw it with a different color. Okay, so the pink line is the actual curve and the white line is the approximated curve. Yes?
If P was much closer to Z, it would look different than what?
Yeah, then there will be some sort of interference between these two peaks and you will see an appropriate change in the Bode plot. Okay? All right. Let me now make a small change to the. So, any questions so far? Okay. So the key thing to learn here is whenever you see a change in the slope of the gain magnitude plot, it implies that there is either a 0 or a pole there. So how would you differentiate between 0 and a pole? If it is sloping upward, it's a 0. If it is changing the slope towards downwards, then there is a pole there. Okay, so if the slope changes by plus 20 dB per decade, there is 1 0 there. If the slope changes up by 40 dB per decade, then there are 2 zeros there. If the slope changes by minus 20 dB per decade, there is 1 pole there. If the slope changes by minus 40 dB per decade, there are 2 poles there, and so on and so forth. Okay. Now let me change it to g of s 1 plus s over p square. Okay, I'm making a small change to the transfer function, in which case this would be minus 180 degrees and this would be minus 40 dB per decade. How do I know? Look at the fifth part of the handout, fifth approximate Bode plot in the handout. And so this is what it looks like. So how will I draw the Bode plot for the updated system? So you don't have to write it down, just look at the board and observe what we are trying to do here. So I start with 20 log k. I hit the first 0. I change the slope to 20 dB per decade. And then I hit the pole P, and there the slope has to change by minus 40 dB per decade. So it's upward sloping 20 dB per decade. I have to change the slope by minus 40. So then I'll have a new slope of minus 20 dB per decade. Okay? And that's because and that will imply that there are 2 poles here at this particular location. It's a double pole. And then the actual magnitude plot might look something like this. Similarly, this phase plot will also change appropriately. And when I hit p over 10, I will start decreasing the phase to minus 180 degrees. So it was at 90 degrees, so the new phase will be minus 90 degrees at 10p, and then it will remain constant throughout. And then the actual curve is going to look something like this. Okay? Yes?
So what if they're complex poles or zeros?
You're talking about complex poles and zeros, right? Okay. So the fact that you have this, so let's say you have a complex pair of poles here. So whenever you have a complex pole, it will always be in a pair. It won't be isolated complex pole, right? Because you're talking about a real system here. So you'll always have a pole, you'll have a complex conjugate pole, set of poles. So you will always have this slope of minus 40 dB per decade, the asymptotic slope. The only thing that will change is depending upon the zeta, what was zeta, damping factor, you will have a small peak here, okay, because of this part, okay. But otherwise the asymptotic properties are not going to change.
So would it change at the real part?
Yes, so it will change only at this point, because if you have a pair of complex conjugate poles, then you will have a resonant frequency, and then the asymptotic slope will be minus 40 dB per decade.
So like if like P was like 3 plus 2J.
Okay. So P was minus 3 plus minus 2J, right? So what is omega n? It is absolute value of P. So that's square root of 9 plus 4, square root of 13.
Oh, okay, so that's
right? So this will be square root of 13. Okay, and this is square root of 13 over 10, and 10 multiplied by square root of 13, and that's where you will have the corner frequency. Yeah, and I'm not lying actually, it turns out. So if you look at the fifth plot, asymptotic plot, you will see that exactly omega n at which the slope is going to change from 0 to minus 40. Okay, any question?
Square root of b?
Sorry?
Does that say square root of b?
The square root of 13.
Okay.
Sorry, this. Okay. So this basically is how you would draw an approximate Bode plot by hand. Now let's do an inverse Bode plot, which is I'm given a Bode plot. Somebody has plotted a log magnitude curve for a system, and I need to identify where the zeros and poles are for that particular system. Remember that Bode plot was very useful for identifying what kind of system you have. So this is perhaps one of the most important part of plotting a Bode plot. So I have a Bode plot that starts from minus 20 dB per decade. One, 10. Okay, so it comes all the way to 1. This is 12 dB, and then I have minus 40 dB per decade. This is the magnitude plot. This is problem 8.6 from the book. The question is find the transfer function. Okay, for this particular transfer function, we are going to assume that all poles and zeros are in the left half plane, so the system is stable. Okay, what does initial slope of minus 20 dB per decade imply?
First order system.
Sorry?
It's a first order system.
No. There is a pole at 0. So G of S, so an initial slope of minus 20 dB per decade implies that there is a pole at 0, and where is that? Okay, and you can see that as number 4 in the asymptotic slope chart. So I have a pole at 0. My slope changes by plus 20 dB per decade at 1. What does that imply? I have a 0 at 1. So let me write it as 1 plus S over 1. And my slope changes at 10 by minus 40 dB per decade. So it was 0 and now it has changed to minus 40 dB per decade. What would that imply? I have a double pole at 10. 1 over 1 plus S over 10 square. And then this is 12 dB, let's say at 6. So I'll have a K term here. And the way I'm going to get the value of K is absolute value of Gj omega, or Gj6 is equal to 20 log absolute value of Gj6 is equal to 12. Okay, I just pick some value between 10 and 1, and then I at that particular omega I set 20 log Gj omega equals to 12, and then I can find the value of K. This can give me the value of K. Should we do it? Would it be easy? I don't know. Let's just do it, okay? I hope it's not very difficult. So what is Gj6? Absolute value of Gj6. So this is absolute value of 1 over 6. 1 over J6. Absolute value of 1 plus J6. 1 over absolute value of 1 plus J6 over 10 square, and into 20 log K. No. Any thoughts what this number will turn out to be? This is square root of 37 over 6, 1 over, what is this? 1 plus 1 plus 0.36, so 1.36 square. So square root of 1.36 square, so that's 1.36 multiplied by k. This is roughly, let's just do some approximation here. This is roughly k over 1.3. Okay, so I have 20 log k over 1.3 equals to 12. So 20 log k over 1.3 equals to 12. This can give you the value of k. This is log base 10. So I have k equals to 1.3 multiplied by 10 raised to 12 over 20, so 0.6. Now you can put it in the calculator and see what the value is. Okay, and this is exactly how people were identifying a transfer function of complicated systems for which they didn't want to do any modeling. Okay, so just by looking at the Bode plot, they can figure out what the transfer function of the system looks like. And all it requires is figuring out where the slope changes for the transfer function. This wouldn't be possible with polar plot, for instance. Or I shouldn't say this wouldn't be possible. Perhaps somebody did figure out how to do it for polar plot, but it would be much more complicated for polar plot. And it's so much easier by looking at Bode plot to identify the transfer function just by looking at the magnitude plot. Okay? Any questions? Okay. Now I want to talk about a very specific situation where you have a 0 in the positive half plane, or a 0 with positive real part. How does that change the whole thing? So in order to do that, let's look at the pole 0 diagram of a system and see how it affects the log magnitude curve and the phase plot. So let's say I have S plus Z over S plus P. S minus Z over S plus P. So I have a Z in the positive half plane and I have a minus P in the negative half plane. S plus Z over S plus P. Okay. I want to find the phase of Gj omega, angle of G1 j omega. So how do I find the angle? Not very difficult. So here is my j omega point. Phi1, Phi2. theta 1, theta 2. So what is angle of G1 j omega? This is angle of j omega minus z minus angle of j omega plus p, which is equal to theta 1 minus theta 2. Okay, so this is the vector j omega minus z, and the angle of j omega minus z is the angle this line segment makes with the horizontal axis, so that's theta 1. Same thing, the vector j omega plus p is this vector, and the angle it makes with the horizontal is theta 2, and so the angle of g1 j omega is the difference of these two angles. Same thing here, angle of g2 j omega is phi 1 minus phi 2. What's the interesting observation here? So what happens when omega is very small? Okay. So when omega is very small, I am here. So the angle of g1 j omega is 180. What about angle of g2 j omega? So when omega is small, phi 1 is 0, phi 2 is 0. So this is 0 for omega equal to 0. Okay, so that's the interesting part here. So if you have a 0 in the positive half space, your phase is 180 degree, but the phase for 0 in the negative half space is 0 degree. What about magnitude? So 20 log absolute value of g1 j omega, what is that equal to? It's 20 log omega square plus z square over omega square plus p square. Same thing here. Okay. So now we have everything we need to, oh no, we also need angle at omega going to infinity. But should we do that now? Let's do that now. So what's angle of g1 j omega when omega goes to infinity? It's theta 1 will be almost 90 degrees, theta 2 would be almost 90 degrees when omega is going off to infinity. So the angle is going to be 0. And in this case, the angle is going to be 0 for omega going to infinity. Okay, so for large values of omega, the angle here is 0. For large values of omega, the angle here is 0. So for omega very, very large, the angle seems to be pretty similar. But for small values of omega, the angles are very, very different. The phase is very, very different. Okay. On the other hand, if you look at the magnitude is the same. There's no difference. Okay. So if I show you a Bode plot for a transfer function, if I just give you the log magnitude graph, we just showed that if you have the log magnitude plot, you can figure out where the zeros and the poles are, right? What's the numerical value of the 0 and the pole is. However, whether 0 is in the left half plane or the right half plane, you will not know until you actually see the phase plot, and that's where phase plot becomes important. So you know what the well, let me draw the Bode plot for both these, or let me draw the phase plot because the magnitude plots are going to look the same. So the phase plot, this is angle of G1, would look something like this. Angle of G2 would look something like this. This will be your Z. Oh, actually this won't be your Z, it will be some point in between P and Z. Let me think about it. Yeah, so Z will be here, P will be here. So Z will be here and P will be here. Okay, so the way to figure out whether you have a 0 in the positive half plane is to look at the phase plot and see whether the change in the phase is going from having a change of the order of 180 degrees, okay, from low frequency to high frequency. In this case, from going from low frequency to high frequency, the change is 0, and the maximum phase gain that you see at any point is sort of not even close to 180 degrees. So this would be 60 degrees, 70 degrees, something like that, but not 180 degrees. Yes?
So earlier on, didn't we discover that a pole will make the phase angle start decreasing? So like in that case, why wouldn't the P be at?
Well, so the 0 is going to start making the phase going up, and then the pole is going to start making the phase go down. So pole has to be.
Would it be where it starts going down though?
Yeah, it will be where. So the interactions between the 0 and the pole is somewhat of a complex one. So we'll have to figure out where the peak is, and that will decide whether these 0 and the poles are close apart or they are far apart. Okay, so if they are far apart, this angle would be around 60 degrees. If they are close to each, if they are far apart, the angle would be 90 degrees. The peak angle would be 90 degrees. If they are close apart, then the peak angle would be less than 90 degrees, but it could be 60, it could be 50, depending upon how close or far they are. Okay, but in this case, since you see that the slope is going upward and then it's going downward, the 0 will have to come first and then the pole will come in. Okay. All right. So then it leads me to the definition of minimum phase and non-minimum phase system. So minimum phase system G is minimum phase if all zeros have negative real part. Non-minimum phase system G is non-minimum phase if there is 1 0, there is at least 1 0 in the positive half plane, or 1 0 with positive real part. Okay, and the way to differentiate between a minimum phase and a non-minimum phase system is not by looking at the magnitude plot, because that wouldn't give you any information about whether the 0 is in the right half plane or the left half plane, but by looking at the phase plot, because that will tell you whether so a non-minimum phase will have a maximum phase change which is small. A minimum phase system, a minimum phase system, so this is the minimum phase, because the change in the total phase across the entire spectrum is very small, it's of the order of 60 degrees, and this is non-minimum phase because the change in phase angle is almost of the order of 180 degrees for this system. Okay. Phase change 180 degrees, phase change 60 degrees across the entire spectrum. Okay, yes?
In the phase plot on the left, so the zeros, I thought the zeros like increase the angle. So in that case, like the one on the right, I understand.
Yeah, let's look at this. Okay, so when j omega is close to 0, this is 180 degrees. When I increase the value of j omega, this is theta 1 which is less than 180 degrees, theta 2 which is less than 90 degrees, and so I have theta 1 minus theta 2, so that will be less than 180 degrees.
Yeah, I understand it that way. It just
Yeah.
seems to contradict with
That's for minimum phase system.
Okay.
Yeah, so this is for minimum phase system. So you can't trust this plot for non-minimum phase. Okay. There was a question right here.
What if they're both positive?
Sorry?
What if they're both in positive plane?
Oh, so then Bode plot is not defined, because remember, for frequency response we required all poles to be in the negative half plane.
Just to clarify, that says a system G, right? Not zeta? It's system G.
Yeah, system G. That's the transfer function of the system. Yeah. Yeah. You have a question about that, or?
No, I was curious. And then also another question was, basically, if it has a positive real part,
Mm-hmm.
that doesn't mean it's unstable? Or
It's a 0, not a pole.
oh, right, okay.
Okay, so 0 can be anywhere, but pole has to be in the negative half space. Okay. All right, any other question? Okay, so far we have talked about what are the different plots, and specifically we have spent quite a bit of time on Bode plots for linear time invariant systems. But we haven't yet talked about understanding the stability properties of a linear time invariant system just by using the frequency method. So that's what we are going to do in the next class. We're going to talk about Nyquist plot. So that's another plot, and see how to assess the stability of a closed loop system by using Nyquist plot. And then we'll talk about gain margin and phase margin, which is useful for designing closed loop controller for systems using frequency domain techniques. So thank you very much. I'll see you guys on Friday.